Optical tweezers. That's the name we give to a system wherein a focused beam of light is used to trap a small sphere of glass or plastic. The beam of light has the highest intensity in the center and fades out as it gets toward the edges. For even greater control, the light can be focused at one point using a convex lens. But how does this work? If light doesn't have mass, how can it support the weight of a sphere that does have mass? Although light doesn't have mass, it does have energy. And this energy is what gets used when supporting this tiny sphere. Light is an electromagnetic wave. It consists of a magnetic field and an electric field undulating perpendicularly. When a photon of light hits an atom, an electron absorbs this energy and moves to a higher energy state. This energy gets released when the electron goes back down to a lower energy state. Because the electron is a charged subatomic particle, there's a change in the electric field it generates when it moves between energy states. A changing electric field corresponds to a changing magnetic field, thereby causing an electromagnetic wave that travels through space. The energy light carries is proportionate to its frequency. For example, because purple light has a higher frequency than red light, it has more energy. This energy in turn has momentum. The momentum of light is Planck's constant divided by wavelength. Combined with the formula for wave speed and photon energy, it yields that the speed of light times a photon's momentum is the photon's energy. Now back to the tweezers. The sphere tends to stay in the middle of the intense beam of light because of how the light diffracts when the sphere moves away. The spherical object bends the light in the direction towards which it moves away. Conservation of momentum pushes the sphere back towards the center. Essentially, Newton's third law still applies. Each action has an equal and opposite reaction. At this point, the sphere is locked within the beam of light. However, the ball still moves away from the light because it's getting pushed by the light. There are two ways we can overcome this problem. 1. Have another equally powerful beam of light, keeping the ball still from a different angle. 2. Focus one beam of light on a single point. The second choice is better because we would only need one light source. By focusing the beam of light, the forces pushing the ball directly away from the source of light are decreased, while the forces holding in place are increased. When the ball moves away from the focus, an imbalance of forces brings it back in. From DNA to microchips, all sorts of stuff can be attached to transparent spheres for accurate and precise movements. Next time you have a big problem, the answer may lie in thinking small.